Welcome to the 14th lecture of module 5 of mass transfer operation. In this module, we are discussing distillation operation. Before going to this lecture, let us have a brief recap on our previous lecture. On our previous lecture, we have mainly considered one important topic is the packed tower distillation. In the packed tower distillation, we have seen what are the types of liquid mixtures we can use for packed tower distillation and what would be the conditions of those liquid mixtures. At the same time, we have considered to calculate the height of the tower required, that is Z. And we have seen that it is similar to the packed tower absorption operations, and we have considered the packed tower design based on the volumetric mass transfer coefficient both in the liquid phase as well as in the gas phase, that is K y A dash and K x A dash. So, in this lecture we will consider multi-component distillation. Under which we will mainly focus on bubble point and dew point calculation. The second thing we will consider is the multi-component flash distillation. Then we will consider multi-component batch distillation. We will also consider to find out the minimum number of plates, that is a total reflux. So, then we will consider minimum reflux and finally, we will consider the approximate method or Underwood method to calculate the compositions of the tower and the number of trays required. So, multi-component distillation. So, there are 3 component systems, at least more than 2 component systems. If it is 3 component systems, then graphical treatment is possible using triangular diagram. If more than 3 components are there, in that case graphical treatment is very complicated. For practical application, liquid phase may be assumed ideal, Raoult's law may be applicable, and equilibrium data can be obtained from pure component data. Now, it is unsafe to predict detailed behavior from pure component alone. So, digital computer is helpful for data analysis to predict detailed behavior. The overall approach to solving multi-component problems is the same in many respects as those described for binary systems. So, if we consider overall approach for the solution of the multi-component systems or for the design of the multi-component systems, in many respects it will be similar as those we have considered for the binary system. There is one mass balance for each component and enthalpy balances are similar to those for binary case. So, what we can see here, in this case the mass balance for each component will be 1. For each component we will have one mass balance and the enthalpy balance would be similar to those for the binary case. The equilibrium relationships are more complex for multi-component systems. In particular, the identity of the most volatile component may change with temperature of the systems. Please note that the identity of the most volatile component may change with temperature of the system. Equilibrium data are used to calculate multi-component bubble and dew points. The limiting cases of total and infinite reflux apply to multi-component columns just as they do for the binary systems. So, in this case also we can apply the limiting cases for total reflux and infinite reflux, and that would be similar as we do for the binary systems. Now, rigorous computer methods for solving multi-component distillation problems are available, but the approximate or shortcut methods described here are common for preliminary design, examining the relationship between the design parameters and process synthesis, etc. Although there are rigorous computer methods available for the multi-component distillation problems, but approximate method can be helpful for preliminary design, examining the relationship between the design parameters, process synthesis and so on. Now, number of distillation tower. In a binary distillation, as we know, one tower is used to separate the components A and B into relatively pure components. So, we generally use one tower having several trays which can separate the binary component into fractions, relatively pure component fractions. But in multi-component mixture of n components, we need n minus 1 fractionators which are required for the separation. That means, if we have 3 component mixture, then n is equal to 3. So, we need n minus 1 fractionator, that means 2 columns are needed. In a design, the conditions of the fit are generally known or specified. That means the temperature, pressure, composition and flow rate. These conditions of the feed are generally known or it should be specified at the beginning of the design. The calculation procedure follows two general methods. Let us consider what are those. Method 1, the desired separation or split between two of the components is specified and the number of theoretical stages is calculated for a selected reflux ratio. So, the split or separation between the two components has to be specified and then we calculate the number of theoretical stages based on a selected reflux ratio. It is clear that with more than two components in the feed, the complete composition of the distillate and the bottoms are not known, then trial and error procedure must be used. This is very clear for more than two component systems. In the feed, the complete composition of the distillate and bottoms are not known. So, we should follow the trial and error procedure to calculate the compositions. In method 2, the number of stages in the enriching section and stripping section as well as the reflux ratio are specified or assumed. So, both section, enriching section and stripping section. In addition to that, the reflux ratio has to be specified at the beginning. The number of component is calculated using assumed liquid and vapor flows and the temperature for the first trial. So, what we are assuming, liquid and vapor flows and the temperature for the first trial. This approach is often preferred for computer calculation. In the trial and error procedures, the design method of Thiele and Geddes is often used to calculate the resulting distillate and bottoms composition together with tray temperature and compositions. Now, equilibrium in multi-component systems. Experimental VLE data not known in most multi-component systems, generally computed from available equations or correlations. Ideal behavior may be assumed so that we can apply the Raoult's law. Hydrocarbons of a homologous series form nearly ideal solutions. We have earlier discussed what are the conditions required for an ideal solutions, and we have seen that hydrocarbons of homologous series, they form nearly ideal solutions. We know that Yj star Pt would be equal to Pj star. Yj star is the mole fractions of component J into Pt is the total pressure is equal to Pj is the partial pressure of component J, which we can write Xj into Pj V. Xj is the mole fractions of component J in the liquid phase and Pjv is the vapor pressure of component J, and Pt we can write summation over I is equal to 1 to n Pi, that is partial pressure all the components. So, this is equation 1. Now, if we rearrange these equations, we can write Yj star would be equal to Pj star by Pt. So, Pt as we know it is summation over I is equal to 1 to n Pi star. So, we can substitute here in this case is summation over I is equal to 1 to n Pi star, and this is nothing but Xj Pj V divided by summation over I is equal to 1 to n Pi star. So, this is equation 2, where Pjv, as I have said before, it is vapor pressure of component J at the given temperature. At a given temperature, the vapor pressure of the components are known. Therefore, for a particular liquid composition, the vapor composition can be calculated. Now, if we define alpha ij is equal to Piv divided by Pjv. Here alpha ij is the relative volatility of component I with respect to J, that is vapor pressure of component I divided by the vapor pressure of component J. So, in that case we can write this equation over here as Yj star would be equal to Xj divided by 1 by Pjv summation over I is equal to 1 to n Xi Piv. Once the equilibrium vapor phase mole fractions are known, the partial pressure and the total pressure can be calculated from equation 1. So, if we can calculate the equilibrium vapor pressure, equilibrium vapor phase mole fractions, then and the partial pressure, as well as the total pressure can be calculated from this equation. So, which is shown before, that is Yj star into Pt is equal to Pj star is equal to Xj Pjv, and Pt would be equal to summation over I is equal to 1 to n Pi star. For multi-component systems, the equilibrium data is described by means of distribution coefficient, which is m. For component J, we can write Mj is equal to Yj star divided by Xj. So, this is defined by equation 4, where in general Mj depends upon the temperature, pressure and composition of the mixture. The relative volatility of component I with respect to J in multi-component mixture is defined by alpha ij is equal to yi star divided by xi divided by yj star by xj. As we have seen before from equation 1, it is the yj star into Pt is equal to xi into xj into Pj V, the vapor pressure of component V. So, if we substitute over here, we will get this as Mj divided by Mi divided by Mj. This is equation 5. For ideal solutions at moderate pressure, Mj is independent of composition and depends upon the temperature, as this affects vapor pressure and the total pressure. So, if we consider ideal solution at moderate pressure, in that case Mj we can consider as independent of the composition, but it will depend upon the temperature and the total pressure. Therefore, we can write Mj is equal to Pjv divided by Pt. So, alpha ij is equal to Piv divided by Pjv. Now, bubble point calculations. For bubble point calculations, we know that summation over y I star, that is summation over all the mole fractions in the vapor phase, would be equal to 1. So, or we can write M A into X A plus M B into X B plus M C into X C plus so on up to the nth component would be equal to 1. So, this is equation 8. Now, for component J as the reference component, we can divide this equation with M J. So, if we divide with M J, so then these equations would become M A X A divided by M J plus M B X B divided by M J plus M C X C divided by M J and so on, and would be equal to 1 by M J. Now, M A by M J is nothing but alpha A J, that is the relative volatility of component A with respect to J. So, similarly we can write alpha A J X A plus alpha B J X B plus alpha C J X C and so on. So, this we can write summation over alpha I j into x I would be equal to 1 by m j. So, this is equation 9. Bubble point vapor composition is given by y I, which is equal to alpha I j x I divided by summation over alpha I j x I. This is equation 10. The liquid composition and total pressure is fixed. The calculation of temperature is made by trial and error to satisfy equation 8. So, this is equation 8. So, trial and error method has to be followed to satisfy this equation. For the dew point liquid, summation over x I would be equal to 1 and y A by m A plus y B by m B plus y C by m C and so on would be equal to 1. Now, for component J as reference component, we can multiply with m J both the sides. So, it would be into m J. So, here we can write y A divided by alpha A j plus y B by alpha B j plus y C by alpha C j and so on, which would be equal to summation over y j by alpha I j would be equal to m j. So, this is equation 12 for dew point calculation. Equilibrium dew point vapor composition is given by x I would be equal to y I divided by alpha I j divided by summation over y I by alpha I j. So, this is equation 13. So, for bubble point and dew point, we know the equilibrium composition, vapor and liquid composition calculation, and also we know the distribution coefficient how to calculate. So, now we will proceed with an example to see how to calculate bubble point and dew point. A solution of hydrocarbons at a total pressure of 350 kilonewton per meter square contains 5 mole percent propane, normal propane, 30 mole percent normal butane, 40 mole percent normal pentane and 25 mole percent normal hexane. Now, we need to calculate the bubble point and dew point. The values of m, which can be taken from monograph and which assumed ideal liquid solution. So, we have considered ideal liquid solution and the values of m, the distribution coefficient, can be taken from the monograph. Now, for bubble point calculations, we will obtain a table like this and we will go step by step how to obtain this table. First, we need to estimate of bubble point, that is 60 degree centigrade is chosen, and column 3 over here. So, with respect to 60 degree, the corresponding and the pressure we know 350 kilonewton per meter square. So, the reference component is chosen to be pentane and column 4 lists the relative volatility. In this case, you can see the relative volatility, that is with respect to the component 5, which is the reference component. So, alpha I C5 is the relative volatility of component I with respect to component 5. So, initially 60 degree temperature is chosen and the data for the distribution coefficient is taken from the literature, and then we have calculated, these are the mole fractions given in the problems, that is 5 mole percent normal propane and then 30 mole percent is normal butane, which is here, 40 mole percent normal pentane and 25 mole percent normal hexane. So, these are given. First column represents the component, second column represents the mole fractions, and the third column which represents the distribution coefficient, and we have assumed the temperature 60 degree centigrade, and then we can obtain the distribution coefficient from the monograph. Column 4 you can see is the relative volatility, and which can be calculated with respect to the reference component, which is 0.62. One calculation is shown over here. In this case 4.70 for normal propane, and for normal pentane it is 0.62. So, we can write 0.70 divided by 0.62. So, this is 7.54, which is written over here. Similar for the other case, we can also calculate in this table. Now, summation over all the components over here in column 5, we can calculate the sum over here, which is summation of all this. It will give about 1.702. Now, we know that Mj is equal to 1 by summation over alpha ij xi. So, this alpha ij xi, that is alpha I summation over alpha I C5 xi is equal to 1.702. So, 1 by that values would give us MC5, which is Mj. So, MC5 is 0.588. So, we can calculate this. Now, with respect to this distribution coefficient values, corresponding temperature can be obtained from the monograph. So, which is shown over here. So, we can calculate this temperature based on this data, distribution coefficient data. Once we obtain this temperature from the monograph, we can calculate the distribution coefficient of other component at that temperature and the pressure mentioned. So, which is shown over here, it is 56.8 degrees centigrade. Now, the calculation are repeated for this temperature in column 6 to column 8. So, similar to the earlier one, 6 at this temperature, once this is known, we can calculate the summation of this, and which would be 1.707, and with respect to that we can calculate MCJ MC5, which is 0.586, which is written over here and which is close to this temperature, and corresponding to that we have 56.7 degree centigrade, which is nearly equal to the 56.8 assumed. So, further calculation has not been done, based on that this has been calculated. So, this is how we can obtain the bubble point temperature. This is the bubble point temperature, and corresponding vapor composition is given in column 9 over here, which is 0.229, and we can calculate the other compositions. Now, we will consider the dew point calculation. So, for dew point calculations, similar to the bubble point calculations, we will follow the calculation procedure in case of the dew point calculation. Now, we need to assume a temperature, say 80 degree centigrade temperature, then we can calculate y I by alpha I 5. So, which is over here, which is 1.081. So, like the bubble point, in case of the dew point we have to assume the temperature. At the temperature we have to calculate the distribution coefficient. Once this is noted, we can calculate the relative volatility with respect to this, and then once this relative volatility is obtained, we can divide the mole fractions with the relative volatility, and we can obtain the data as shown in column 5. So, once this is obtained, then we can see the temperature is 83.7, which is obtained corresponding to the values of 1.081, which is shown over here. So, corresponding to this distribution coefficient values, we can choose the temperature, and then we can calculate the other distribution coefficient, and this process is repeated and shown in the other columns, and it was seen that the temperature which was obtained is close to the assumed temperature in this case, so that is 83.7. So, this is the dew point temperature. Now, we will consider multi-component flash distillation. As we have defined before, in case of the flash distillation, the fraction of the feed vaporized F is equal to V by F. The small f is equal to V by F. Fraction of the feed remaining as liquid is 1 minus F, which is equal to L by F. Now, if we do the balance on component I, we can write y I is equal to F minus 1 divided by F into x I plus x I F divided by F. So, x I F is the feed composition or feed concentration of component I. Y I is the composition of I in the vapor in equilibrium with x I, which is in the liquid after vaporization. So, this is equation 14. Now, because a flash is a single equilibrium stage, equilibrium fixes another relationship between y and x. Combining equilibrium and operating equations, that is y I is equal to k I x I is equal to k C alpha I x I, where alpha I is k I by k C. K C is the equilibrium constant and k I is the distribution coefficient. So, now the component balance equations we can write y I is equal to k C alpha I x I, which would be equal to 1 minus f by f into x I plus x I f by f. So, this is equation 15. Now, solving for x I and summing for all components, if we do that, summation over x I would be equal to summation over x I f divided by f into k C alpha I minus 1 plus 1 is equal to 1.0, because the summation over all components is equal to 1. Solved by trial and error by first assuming a temperature if the fraction f vaporized has been set. So, we can set the fraction vaporized, which is f, then we can assume a temperature and then solve by trial and error. When the summation over x I values add up to 1, the proper temperature has to be chosen. The composition of the vapor, that is y I, can be obtained from y I is equal to k C alpha I x I. So, once that is temperature is obtained, then we can obtain the composition of the vapor using this relation, or we can do by a material balance relations. The iteration procedures similar to bubble point and dew point for this multi-component flash distillation. So, what we need to do? We need to assume a flash temperature, determine k values at that temperature, and then compute the summation. If the summation is not equal to 1, adjust the temperature and repeat. The final values of T and the K's are used to determine the product composition. Now, let us consider an example to discuss the flash distillation. A mixture of hydrocarbons containing 32 mole percent of N-hexane, 38 mole percent of N-heptane and 30 mole percent of N-octane is subjected to a flash distillation at 1.2 atmosphere pressure. 40% of the feed is to be vaporized. Find the temperature of the flash and the composition of the liquid and the vapor products. Consider the bubble point temperature of 97 degree centigrade and the dew point temperature of 110 degree centigrade. The data, the vapor pressure and the temperature data are given in this figure. So, this is the temperature vapor pressure data. So, the flash temperature in this case would lie between the bubble point temperature and the dew point temperature. Now, assume T, which is flash temperature, would be equal to bubble point temperature 97 plus 40% is vaporized, that is 0.4 into the dew point temperature 110 minus 97, that is the bubble point temperature. So, this would be equal to 97 plus 0.4 into 13, which is equal to 97 plus 5.2, which is 102.2 degree centigrade. Now, if we look into the figure, this figure at 102 degree centigrade temperature, say over here, if you can go off, you will obtain for vapor pressure for octane is about 0.5. Similarly, for N-heptane is about 1.1, and again if you go off over here, so you will obtain is about 2.5. So, from the figure we can write vapor pressure at that temperature is for C NC5 is about 2.5 atmosphere. Similarly, for NC6 is 2.5, NC7 is about 1.1 and NC8 is about 0.5. Now, we can obtain the K values, that is K NC5 NC6 would be equal to 2.5 divided by the pressure of the operation, that is 1.2 atmosphere. So, which is equal to 2.08. Similarly, K NC7 would be equal to 1.1 divided by 1.2, which is equal to 0.92, and K NC7 NC8 would be equal to 0.5 divided by 1.2, which is equal to 0.42. Now, we know that summation over xi is equal to 1.0, which is equal to summation over xif divided by fraction vaporized F into Ki minus 1 plus 1. Now, if we consider a right hand side of the equation, we can write 32 mole percent of N-hexane. So, x in the feet, so xif would be 0.32 divided by 40% of the feed is vaporized. So, F would be 0.4 into Ki for component NC6, as we have calculated K NC6 is equal to 2.08, K NC7 is equal to 0.92 and K NC8 is equal to 0.42. So, if we substitute this 2.08 minus 1 plus 1. Now, for the component heptane NC7, we can write plus which is 38 mole percent. So, 0.38 divided by 0.4 into 0.92 minus 1 plus 1 plus for component N C8 which is 30%. So, it is 0.3 divided by 0.4 into 0.42 minus 1 plus 1. So, this would be equal to 0.32 divided by 1.432 plus 0.38 divided by 0.968 plus 0.3 divided by 0.768. This would be equal to 0.224 plus 0.393 plus 0.391, which is equal to 1.008. So, this is close to unity. Hence, flash point temperature is equal to 102.2 degree centigrade. Now, the liquid composition, as we can see from this relation. So, this is from here we can get the composition of the N hexane and this is the composition of N heptane and this is the composition of N octane. So, liquid composition NC6 is equal to 22.4%, NC7 is equal to 39.3%, NC8 is equal to 39.1%. Now, the composition of the vapor product is computed from the values of Ki and Xi. As we know, Yi is equal to Ki Xi. Now, N hexane NC5 Y vapor composition would be 0.224 into 2.08, which is Ki. As we know, K NC6 is 2.08, K NC7 is 0.92 and K NC8 is 0.42. So, this would be equal to 0.466, then N heptane, that is NC7 is equal to 0.393 into 0.92, which is equal to 0.362, and N octane, this would be equal to 391 into 0.42, which is equal to 0.164. If we sum up, it would be 0.992. So, this is the vapor composition and this is the liquid composition. So, this way if we have the bubble point and dew point temperature and the composition of the mixture and the pressure of the operations are mentioned, we can calculate the flash point temperature and as well as the liquid and vapor compositions. Now, we need to consider the key component for multi-component distillation. Select two components to serve as heavy key and the light key. Key component must be present in both the overhead and the bottoms. Please remember that key components must be present both in overhead and the bottoms. Then light components we can define as the more volatile than the light key are called the light components and will be present in bottoms in small amount. Heavy components less volatile than heavy key and present in distillate in small amount. Two key components are present in significant amounts in both distillate and bottoms. So, please note that the two key component should be present in significant amount in both distillate and bottoms. Now, non-key components, that is everything but the keys. That means, it may be distributed if they occur in both products, that is bottoms and the distillate, or non-distributed if they appear in only one product, that means either in bottoms or in vapor or in distillate. They are called non-key components. Remember, keys must be distributed, that is heavy key and light key, they must be distributed and they should present in both distillate and bottoms in significant amount. Non-key may be distributed when they have volatilities very close to the keys or between the keys and when desired separation is sloppy. So, in this lecture we have discussed the introduction to the multi-component systems and then number of tower required for a multi-component systems, different calculation methods, equilibrium in multi-component systems and bubble point, dew point calculations, multi-component flash distillation and concept of key components and minimum number of stages. So, thank you for attending this lecture and we will continue our discussion on multi-component system in the next lecture.